In this section, we're going to take a look at several different concepts about line integrals and some of their applications. What we're going to see here at the start in example 1 is going to be kind of a nice motivating example to help us understand the types of questions we want to start to ask in this section. So take a look here at example number 1. Let's suppose that C1 is given by this vector function, r defined by t, where t goes from 0 to 1. And suppose that C2 is given by a different parameterization, t comma t squared. T again goes from 0 to 1. So part A, where do the above curves ultimately start and end? Well, that's actually super easy to see because we can just plug in 0 as our starting point and plug in 1 as our stopping point. That seems to be true for both these curves. And we can see that both curves start at the point 0, 0, right? When I plug in 0 for t, I get 0 and 0 back for both x and y in both these formulas. And they end at 1, comma 1. Okay, so this is kind of interesting. I might notice again that this first curve up here can be thought of as the curve y equals x, whereas this curve over here can be thought of as y is equal to x squared. And so, of course, it's no surprise that from 0 to 1, both these curves kind of have the same starting and stopping points, even though they move along different paths to get there. Okay, so here's the question that we want to go ahead and work with here in part B. Can I show that when I integrate along C1, which is going to be the line, and I integrate along C2 in these integrals, I end up showing that these two things are equal? Now, I'm actually going to ask you to try to do this. So I would encourage you, pause the video, see if you can actually verify that both these things come out as the same answer. And once you unpause, you'll see me go through the same calculations. You can use that to double check your work. All right, so if I was going to do this, I would say that for C1, we have that the integral across C1 is going to be equal to, let's see, I'm going to integrate from 0 to 1 there. My y in that case is just a t. My dx is just going to be a dt. My x is a t, and I get a dt. So this is really just the integral of 2t dt. So that's t squared evaluated from 0 to 1, which is just 1. Okay. For C2, we have the integral of C2 for y dx plus x dy. That's still an integral from 0 to 1. My y there, though, is a t squared. My dx is a dt. And my x is a t. My dy is a 2t dt. If I was to simplify this all the way down, I have an integral from 0 to 1, and I have, it looks like a 3t squared total. This ultimately turns into a t cubed, evaluate from 0 to 1, and I get 1. So I can definitely confirm that these two things here are equal. Notice that these are like two work integrals that we talked about in the last section. And interestingly, even though I have a different path that's leading me from 0, 0 to 1, 1, I ultimately produced the same result. So the question that we would pose is, what if we were to take any smooth curve from 0, 0 to 1, 1? Would we have still gotten that when we would have taken y comma x dot dr, would that have still been 1? I mean, maybe, maybe not. I can imagine a lot of other curves that go from 0, 0 to 1, 1, maybe like x cubed. Would that have changed the answer? So questions like this are actually going to be the theme of this entire section. How is it that I would know and be able to confirm whether the path that I take to get from my start to my stopping point, whether that matters in terms of does it change my answer or does it not change my answer? In the next video, we'll take a look at a theorem to help us understand that, and then a bunch more examples.